This would be a good time, if you haven't yet, to take a look at my table on the screen to verify that your values match mine, because we're going to need those values to answer questions B and C next. Also, this would be a good time to make a quick observation about the math that you did, because if you showed your work, or at least followed along with my examples, you'll see what I was alluding to in an earlier video about the dummy variable t. Did you notice how no matter which problem you were doing, you ended up plugging in the py/6 and the 0 or whatever the upper and lower limits were, and t didn't end up being part of your answer? That's a big part of the reason why we call it a dummy variable, is because it's really just there as a placeholder until you plug stuff in. And since fundamental theorem problems are all about plugging something into the integral, that's why we don't really care what t is. It's just kind of a temporary placeholder spot that's showing us where the plugging in is going to happen. So going forwards, please don't be confused by the fact that integral problems have a t in them. Just note that that's the dummy variable, and you're going to end up plugging something into that spot anyway, so don't spend too much time fixating on the letter t. A common mistake that students make, especially at the college level, is to always write everything with x as the variable, because they've gotten so used to, over the years, using x in algebra, and then in algebra 2, and then in math analysis, so by the time they get to calc, it's just so easy to default to the letter x as our go-to variable for everything. You just have to pay attention, because you don't want there to be two x's in a problem. You don't want x to be the original input you were plugging in, and a different variable somewhere else that you're not plugging in. That doesn't make any mathematical sense. So that's why you just have to be consistent. You just have to pay attention. Nevertheless, here we are also paying attention to our work, noticing every time we did this, we did the exact same thing. We ended up getting the same antiderivative every time. It was always sine t. And no matter what we plugged in for the upper limit, the lower limit was always 0. So really, it was just the upper limit that seemed to be driving most of our work. And if you got to the point where you're like, oh my gosh, Herbert, this is so tedious. Do I really have to show all these steps? I hope that you answered to yourself a very simple question. No, of course not. Sine of π/6 is 1/2. I didn't really have to write all of this to know that the antiderivative of sine, plug in π/6, plug in 0. Oops, don't care about plugging in 0. Sine of π/6 is 1/2. Boom, done. So by the time that you finished your table, hopefully you did notice, and this is part B, that all of these values are simply the sine values for those individual x coordinates. Sine of 0 is 0. Sine of π/6 is 1/2. Sine of π/4 is √2/2. And if that made faster work of your table because you noticed that kind of early on, that's great. These are basically all just sine x values, not fancy antiderivative values after all. Now, ultimately, in letter C, it says, show how to use the fundamental theorem to find the antiderivative algebraically, and you might be thinking, well, I just did that. But technically speaking, we actually could have figured out that this was just a sine problem in one other way, and that was if we found the antiderivative from 0 to x of the original cos t dt without actually knowing what x is. In other words, even if x wasn't a fixed endpoint on a graph, we could still tell how to go through the fundamental theorem and how to figure this out. If you think about it logically, remember, the function itself is cos t. The antiderivative of cos t is always going to be sine t, no matter what. And if I go through the motions of the fundamental theorem, that means I write my antiderivative, sine t, evaluated at the upper limit and the lower limit with my little vertical bar there. Now the upper limit is a variable, but who cares? We know that the fundamental theorem is always the same every single time. We plug in the upper limit, we plug in the lower limit, and then we subtract the values. Now it looks a little peculiar here because sine x minus sine 0, those don't look like numbers that we're used to, but sine 0 is still 0. So sine x minus 0 is simply sine x. And that simply goes to show that you can do an antiderivative problem even if you don't know what one of the limits is. If you can just go through the motions of the fundamental theorem, you can totally just do the antiderivative anyway. So with problems like these that have two variables, t and x, don't let it faze you. Just go through the motions. That's really what the moral of the fundamental theorem is all about. Just go through the motions and plug stuff in. If you can do the antiderivative in terms of t, and if you can plug in your upper and your lower limits, going through the motions should yield you an answer. Your answer is not going to be a whole number or any sort of numerical value. Your answer is going to look kind of like a function, but that's okay. Your answer is going to be in terms of x, and that's actually what an answer to a fundamental theorem problem often looks like. It just looks like something in terms of x. So keeping that in mind, because it might feel a little unsatisfying, like, oh, what, like, wasn't I supposed to get something? Wasn't there supposed to be a cool result? Bear with me here, because as we continue to flesh out the ideas on the next page, which is page 7, I want us to just start to kind of build slowly the idea that we know what we're doing. We have this antiderivative process. We know how to plug in and evaluate it, so that as we layer in new information, we're building on a foundation that we feel pretty solid about. Question number 2 is going to keep building on this idea. So let's roll into question number 2 knowing, okay, we know how to do the fundamental theorem. We take an antiderivative, that's step 1, and we plug in its limits to subtract. That's step 2. That's all we need to know about the fundamental theorem right now. There is a phrase up here at the top of page 7, by the way, that's called accumulation. I'll get into that closer to when we do the next lesson, which isn't till the end of this week, because accumulation is yet another word that's kind of lumped in there with antiderivatives and areas. And right now I don't want to overload us with too much new vocabulary. So if you want to read this little bit about accumulation, you can. It's not really that essential. I'm going to skip it just for the sake of cohesiveness, and I'm going to recommend you do the same if you already feel like this is enough new info at once. Let's just jump straight into question number 2, and let's practice using the fundamental theorem, because it specifically says in question 2a, use the FTC, use the fundamental theorem, which again is a 2-step process. Take the antiderivative, then plug in and evaluate your limits. That's what the use the fundamental theorem direction means. So this is a familiar looking problem. This is a power rule problem. I don't have to do any fancy U subs or anything because I have 3 disparate terms. Each of them has a power rule setup, so nothing fancy. Also noticing that t is the dummy variable again. That's pretty universal. We know that t is not going to be an issue in our answer. So I'm just kind of noticing it, but not making a big deal out of it. So let's use the fundamental theorem again. We need to find the antiderivative of each individual term. So the antiderivative of t squared is 1/3 t cubed. The antiderivative of minus 4t is minus 2t squared. And the antiderivative of plus 1 is plus t. Now remember, with these problems, I don't write plus c because I have limits. These are the definite integrals that have limits to evaluate. So I write my evaluated bar with my upper and lower limits to plug in. Hopefully you're with me so far. Hopefully you can see what I've done. That was step 1 of the fundamental theorem, which is take the antiderivative. Step 2 of the fundamental theorem is to do the plugging in part. So this is where I'm going to plug in my upper and lower limits. Usually to do that we just write equals, and then we show that step either underneath or to the right of wherever we wrote this antiderivative out. So I'm going to start with the upper limit. We always start with the upper limit and plug that in. So I'm going to have 1/3 x cubed minus 2x squared plus x. I'm really just plugging in x for t, so it almost feels like a superficial step, but here we are. Then I'm supposed to do minus, and I'm going to plug in 1 into all of those variable spaces all over again. You'll notice I'm using parentheses here just to kind of group things together, because plugging in x left me with a bunch of terms, plugging in 1 is going to leave me with 3 separate terms, and because I have to subtract, I'm using parentheses to kind of group things together so that subtraction sign doesn't just get lost. Now when I plug in 1, 1/3 times 1 cubed is 1/3, minus 2 times 1 squared is 2, plus 1 plugs in for t, so that's 1. So now I have something I actually have to evaluate. This time I actually do have a number that I'm going to have to subtract. So I can tell this answer is not really going to work out very nicely. I don't have a lot of like terms that I can subtract, so I'm just going to clean this up and hope for the best. If I clean up the beginning part, I don't have any like terms to combine. So I have 1/3 x cubed minus 2x squared plus 1, but then I can clean up this a little bit. 1/3 minus 2, would be 1/3 minus 6/3 if you're a common denominator person. And then plus 1 would be plus 3/3. So that might be a quick little bit of side work that you can do if you have trouble with fractions and aren't good at visualizing them. 1/3 minus 6/3 is negative 5/3. Negative 5/3 plus 3/3 is negative 2/3. And I'm looking that's a little bit more, saying to myself, okay, can I do anything? Oops, that was an X, my bad. I don't see anything I can do. This must be my answer. I've subtracted, I plugged in, I've done everything I'm supposed to do. That's about as far as I can go. So if it feels unsatisfying because your answer doesn't look like an actual area, it doesn't look like an actual number, don't worry too much. When the original problem had 2 variables, I mean, the fact that we got any answer is pretty darn good. We didn't expect an answer of a whole number or any specific value because there was too much unknown in the problem. We really didn't know. We didn't know what t was, we didn't know what x was. The fact we got anything, darn good enough. So let's stick with that. Now, in letter B, it says take the derivative of your answer in part A. So that's kind of interesting. It's asking us to follow up with our answer to part A, that answer that we said, I don't really know what that's supposed to mean. Letter B is like, no worries, take its derivative. So this is kind of interesting because that I haven't really done in a while, but derivatives, like old school derivatives. This will be a great opportunity to review that skill. Let's take the derivative here. I'm just going to label it. Usually I would have a prime, but I don't really have any good notation going right now for derivatives, so I'm just going to kind of wing this. But let's take its derivative. The derivative, so I'll just call this ddx or something like that. They say in letter B, this whole thing, I'm just feeling kind of lazy to copy it all out, so I'll just say derivative equals, this is not great notation, but we're taking some liberties just for clarity. The derivative of 1/3 x cubed. Regular derivative power rule here, bring down the 3, that's going to cancel, so I have x squared, minus, bring down the 2, that becomes 4x, plus derivative of x is 1, derivative of minus 2/3 is nothing, that's 0, so there's my derivative. And in letter C, I'm supposed to notice something. I'm looking at this, again, feeling unsatisfied, but then saying, hey, wait a minute. X squared minus 4x plus 1. That looks a lot like the original function. T squared minus 4t plus 1. Other than the fact that the variable has become x instead of the original t, I have the exact same thing I started with. And if you weren't really expecting that, or if you never really noticed that, this is a great time to ask yourself, how could that have happened? How did we circle back to the exact same structure we started with? But think about it for a moment. We took an antiderivative, then we took a derivative. We did 2 opposite operations. We took an antiderivative, then a derivative. That's like adding 5 and then subtracting 5. Or multiplying 10 and then dividing by 10. We did 2 inverse operations. Inverse operations cancel each other out. So we did something and then we undid it. So it does actually make sense that we ended up with something eerily similar to what we started with, because by doing an antiderivative and then undoing it, of course we're going to end up back where we started. That actually makes perfect sense. The only interesting effect of doing the antiderivative and then undoing it is the fact that the variable changed. And that was a result of the fundamental theorem. That was a result of plugging in x in the first place. And then when we took our derivative, it was in terms of x. So that was why we ended up with a derivative that had x's instead of the original t's. But that's okay. Remember that t is a dummy variable? We don't care about it. It's actually okay that at the end we end up with an answer with x. That's actually supposed to happen. That's totally fine. The structure is the important part. Something squared minus 4 times something plus 1. That is the part that we're supposed to notice. So the general observation that you might want to record in your own words here in number 2, letter C, is that we have essentially done an inverse operation, or we've done something that canceled itself out. We did an antiderivative, and then we did a derivative, and we ended up back where we started. That really is the core of the second fundamental theorem of calculus that gets formalized down at the bottom. So before I start the next video, I'm going to ask you to stop this one and take a few minutes to just process, make sure that you followed the logic here, and if anything, maybe read ahead to kind of see if you can preview where this is going, because this is kind of a formality. It doesn't really help us solve anything, but it's an important observation to make, that By taking an antiderivative and then doing its derivative, we ended up back where we started. It might seem trivial to you, like, well, duh, of course, that's just how algebra works. But it's the real crux of what this whole section is about, this second fundamental theorem of calculus, so I want to make sure that it makes sense, even if it's very trivial or easy to you. Take some time to just chew on this, make sure that you followed our logic, and then in the next video, I'll try to kind of piece it together in the more abstract sense.